Well, here we are again in ELE 210. And we're talking about power ratios and decibels. And I don't know if you've seen this in one of Professor Millet's classes, but if you have, that's great. And if you haven't, we're going to cover it now anyway. So, in signal processing systems, we often care about the power going into one of the blocks of our systems and the power coming out. Here's an example where it's an amplifier. I'm going in with 1 milliwatt and coming out with 100 milliwatts. And, you know, so we have a power gain, which is a power ratio. It's P out over P in. 100 milliwatts over 1 milliwatt, that's 100, pretty simple. And here we have an attenuator where we come in with 4 milliwatts, we come out with 1 milliwatt, so maybe you could still call it P gain. I just called it P at 10. P out over P in, 1 over 4, 0.25, not a lot of complication there. Now, signal processing and most natural and physical phenomena seem to benefit from discussing power ratios in exponential terms instead of simple ratios. And I think we could probably say here exponential or logarithmic terms. And what this comes from is it typically, in order to get a larger effect in some natural systems, the amount of power that you need to add or take away seems to depend on how much power is already there. So if you want to signal somebody in the presence of a lot of loud noise or something, you need to put in a lot more power than if the environment were quiet. And it seems that power, it's not linear. It's just, you know, it's not like you know, if it's twice as loud or and that type of thing. The amount of power it takes seems to go up exponentially. And the way we sense things as humans and the way other you know, sensing systems seem to work is, well, we may want a very linear transfer function in some sensors. We may need to discuss what's going on in this exponential and logarithmic world because that's just the way things are, and we would wind up having, I guess we care more about the logarithmic representation than the exponential, but the world is exponential and we reduce that to logarithms, okay? So let's take an example here. First of all, the classic math statement about exponential expressions and logarithmic expressions. If I have x equals 10 to the e is the exponent, 10 is the base. The other expression I can write, you can call it an inverse function if you like, is e is equal to the log of to the base 10 of x, okay? So if you put in 3 here, e equals 3, 10 to the third is 1,000. If I take the log to the base 10 of 1,000, I would get 3. So these are inverse function pair, if you will. And as I keep going down here, a couple of definitions for us. Power ratio, regular power ratio, is equal to 10 raised to the power ratio in Bels. Bels is an exponential, it's really a logarithmic expression of power ratio. So the power ratio in Bels is equal to it's equal to the log to the base 10 of the power ratio, you know, P out over P in. When we express the power ratio take the logarithm of it, we get the power ratio in Bels, or Bell, I guess is the way they say it. And if we were to state that the other way, The linear power ratio could be expressed as 10 to the power ratio in Bels. All I'm doing is I'm making a restatement of well, let's do a better job here, of this expression pair here. Okay, so given that power ratio in Bels, because if we just talk in terms of P out and P in the systems that we have in order to do something, P out and P in, we're going to wind up with some huge numbers here in terms of power ratio, especially say in radio signal paths, RF signal paths where you're receiving maybe a microwave signal and you're going to have to boost that to something where you're going to do something with it, or you're receiving maybe some kind of a radio signal and you're building a repeater and you have to repeat it out to send it to the next station or something. Then in that case you're going to take in a really tiny power and you're probably going to have to blast the antenna with a huge power, and these straight ratios will become huge numbers. By using logarithms we tend to get a system that's a little easier to work with, and after you work with logarithms enough you begin to get used to what logarithms equal what regular linear ratios here. So anyway, these statements are let you know how this whole system of logarithms or exponents works. If we take a look at our, if we take a look at our amplifier example, we come in with a milliwatt, we go out with 100 milliwatts, and the power ratio is 100. If we were to do this in Bell, we would say that the power ratio in Bell is the log to the base 10 of of the linear power ratio, or 100, and the log to the base 10 of 100 is 2. That's 2 Bell. And we can say the power ratio is equal to 10 to the power ratio in Bell, okay, or 10 to the 2, and that gives us 100. So that's how that works. A more typical unit, though, is decibels, because we'd actually like to work in between just powers of 10. So they came up with this unit called the decibel, and there are 10 decibels in 1 bell, or a decibel is a tenth of a bell. So the power in decibels, you just take what it would have been in bells. 10 log to the base 10 of the power ratio is the power ratio in bell. Multiplied by 10, you get the power ratio in decibels. So we get 10 times the log to the base 10 of 100. This would be 2, but multiplied by 10, you get 20 decibels, and the unit abbreviation for that is lowercase d, uppercase b. That's decibels. So another example we can take a look at is our attenuator. It has a P in of 4 milliwatts and a P out of 1 milliwatt. Now the power ratio in decibels there is 10 times the log to the base 10 of P out over P in equals 10 times the log to the base 10 of 1 over 4, which is 0.25. And the log of any number less than 1 will be negative, and we get minus 6.02 dB. A lot of people will just round this off and say that's minus 6 dB. So when you cut the power into a fourth, you get it's a minus 6 dB gain, or you could say it's a 6 dB loss, or however you want to say it. But negative means that it's a power loss. Okay. There we go. So let's consider a typical system has constant input and output resistance. We tend to work, say, in a if it's RF or instrumentation, it's very often a 50 ohm system. If it's a twisted pair type of thing, it's usually a 100 ohm system. Cable TV is a 75 ohm system. But if we're in the same system, One thing that's very useful, it's kind of hard to measure power, but it's not too hard to measure voltage, because you can just put your some kind of voltmeter or oscilloscope across, from the signal line to ground if it's a single-ended signal like we've drawn here. And the input to this 50 ohm input block is V1, and the input to this 50 ohm block, or the output from this one, either it's the same voltage, is V2. So the power being delivered to this guy is V2 squared over 50, V squared over R. The power that's going in here, P in, is V1 squared over 50. Now if I multiply the top and bottom by 50, I got V2 squared over V1 squared, and that is the same thing as V2 over V1 squared. Now a little bit of mathematics here. Again, all input and output resistance equal 50 ohms, so we're able to do this because things are constant. If I want to look at the power ratio of block 1 in dB, I take 10 times the log to the base 10 of the power ratio, which is V1 over V2 squared. Now, whenever you take, if you remember, the log of a product is the sum of the logs. I'll say that again. The log of a product is the sum of the logs. So the log of x squared, that's the log of the product x times x. And that's the same thing there, it's the sum of log x plus log x. And that means the log of x squared is equal to twice the log of x. So we can make our formula, restate our formula now, that the power ratio of block 1 in dB is equal to 10 times 2 times the log to the base 10 of V2 over V1. See, we don't have the square anymore. That square comes out of the log as a 2 over here. So the power ratio block in dB, block 1 in dB, is equal to 20 times the log of V2 over V1. Likewise, the power ratio in block 2 in dB is 20 times the log of V3 over V2, because the output here is V3 and the input is V2. And this all works, there we go, this all works as long as the input and output resistances are equal. You can use this formula, dB, the power ratio in dB is equal to 20 log base 10 of V out over V in. And it's a lot easier to measure voltage than power, so this formula gets used a lot. So I just want to mention a couple standards while we're talking about dB. Gary, Professor Millett will probably talk a little bit more about this. But I would say the most important standard in talking about decibels, well, decibels themselves, you've seen that as a way to express power ratio. dB small m means power ratio compared to 1 milliwatt. So for example, if we have, if the power at some test point 1 in our system is 8 milliwatts, we can say that PTP1 in dBm is equal to our old formula, 10 times log to the base 10 of that power, we probably call that power out, divided by our input power, which here is not really an input power, it's a standard, it's a reference power, okay? So we can think of this as a reference power. We're just comparing everything to 1 milliwatt when we talk about dBm, reference power. And of course it's equal to 1 milliwatt. Okay. So now we take 10 times the log to the base 10 of 8 milliwatts over 1 milliwatt, it's going to be 8. And we get a power at test point 1, is it's 9.03 dBm. That's 9.03 decibels relative to a milliwatt. And like I said before about the 6.02, a lot of people would knock this off and just say 9 dBm, and that's pretty well accepted. This one's a little different. I think this one's just as important. Again, let Professor Millett take the lead here on what units he thinks are most important. dV microvolts shows up in another place, and it's not really a power so much as an output voltage giving a stated power ratio in an equal resistance system where Vin is 1 microvolt. Okay, so if I were to say that an equal resistance system, I guess, we're really saying that 1 microvolt is our standard or reference voltage. So this is a reference voltage, and it's assumed to be in a resistance that's equal to whatever we're using. So this is a reference voltage, and it's 1 microvolt. So let's say the voltage out of our system is 0.5 millivolts. This could be RMS, could be DC, but it's probably a signal. So let's say 0.5 millivolts, and even if it isn't, if it's peak to peak, well, this is really meant to be RMS. So let's be specific here, okay? So I guess this voltage has to be RMS. So if I have 0.5 millivolts RMS, that's 500 microvolts RMS. Vn, the standard, is 1 microvolt RMS. So my power ratio in dB microvolts, you can look at it this way and say that, I'm going to change this here. The power ratio here is just in dB. So sorry I had that in there, but the power ratio is just in dB. Well, let's just use our old formula for power ratio in dB. It's V out is 500 microvolts, which is, and these, let's say these are RMS. Yeah, I'm sure you can see that. So that gives me 20 times the log to the base 10 of 500 as the ratio. And my power ratio in dB, just again, my power ratio in dB to whatever this reference is, if I were to compare it to 1 microvolt, would be 54 dB. The voltage ratio for 0.5 millivolts or 500 microvolts compared to a microvolt, if you were in the same resistance system, that voltage would be called 54 dB microvolt, because it would indicate the same power gain as a 54 dB system if I stuck a microvolt as the input. I hope that is understandable, and I hope I haven't messed that up too much. But dB microvolt gets used sometimes in very, very small signal systems, obviously. But the one you're going to see most often is dB milliwatt. dBm is the power ratio compared to 1 milliwatt. And some of these dB microvolt things, you have to look and see, how it's being measured and that sort of thing. But it's you can look it up, you can find out more about it. But basically, if you've got in our example, if you've got half a millivolt in your system, then that is a voltage that would create a power ratio of 54 dB if you put in a microvolt as your input and 0.5 millivolt were your output. And so they call 0.5 millivolt 54 dB microvolts. So let's just say here, in this case, um, 0.5 millivolt or 500 microvolts is called .54 dB microvolt. Again, it's a way of referring to this voltage right here with respect to a microvolt, because maybe the system is characterized in a certain way, and you could refer to it as this voltage, or you could refer to it as 54 dB microvolt, and that may help in some calculations because you've already kind of considered the thing in a power ratio, from a power ratio standpoint. But if I could put 1 microvolt into the system and get out 0.5 millivolts or 500 microvolts, I'd have a gain, just a straight power ratio gain in dB of 54 dB. And therefore, I can also refer to 0.5 millivolts or 500 microvolts, either way you want to say it. I can refer to it in reference to 1 microvolt. I can refer to 0.5 millivolts or 500 microvolts as 54 dB microvolts. All right, that's a voltage. Even though it's expressed in dB, it's using dB to express a voltage, that's related to a given power gain and related to 1 microvolt. I hope that helps. Okay, and that's it for that discussion on dB. I'll have some homework problems that ask you a few questions on dB, and I'm not trying not to go too awfully far in it because we don't need to. And we probably care way more about dBm. We care more about regular dB as a power ratio in decibels, and maybe some dBm stuff, and that's probably good enough for us, and probably good enough for most audio stuff. If you may see dB microvolts in some real low-level audio stuff. So, yeah, all right. Take it easy, and now this time for sure we will head into to active devices and some interesting circuits there. Okie doke. Have a good time, be safe, and we'll see you again soon. Bye.